Hey, greetings and welcome, friends. Mr. Waddy here. Today we're going to talk about a geometric solid, which is not a polyhedron. It is not made up of individual polygonal faces. It is made up of a single surface, and it's a sphere, which controversy aside about whether or not the Earth is a sphere, it is. At least we can all agree that the sun, the 93 million miles away that it is, that is definitely just a flat circle. But here we go. Let's calculate the volume of a sphere, which, remember, is asking the question how many little, one by one by one cubes could fit inside of that object. And you might realize very quickly that that's hard to do. It's hard to take a smooth, curvy surface and then represent it with cubes, which is why the company that makes Lego has as one of its job interviews for its Lego engineer people to be able to approximate a sphere with their Lego pieces. Hard to do. Let me show you a little animation of an approximate sphere. Okay, so this one's got planar faces right here, little quadrilateral faces. But this is the idea that you can actually approximate a sphere. If I pull out this little orange slice right there, oh man, that makes me want one of those chocolate oranges. I should post a link on where to buy those chocolate oranges online. I'm saying the word oranges a lot, which I realize most people are annoyed at the way I pronounce the word. Wait, how did I say it? Did I say it orange or orange? I think I say orange. Like I'm saying the orange you glad, but whatever. But notice if I take out this little orange slice and cut it up even more, man, it's like soccer practice halftime all over again. I would end up having a whole bunch of little pyramids. And you could actually, using calculus and all sorts of stuff, calculate the volume of all of those pyramids and the number of them that go around and use that to approximate the volume of a sphere. And then what you would do is you would let the size of these little quadrilaterals get smaller and smaller and smaller and subdivide further and further and further until they are, the word is infinitesimally small, in which there would then be infinitely many of these pyramids, and we would then have the exact value of the volume of a sphere. And so it's kind of an interesting little formula, nothing too crazy, but the volume formula for a sphere is 4/3, so the fraction 4 divided by 3, 1.3 repeating, multiplied by pi, makes sense, it's got like circly parts in it and a radius, times the radius, and check out this, look out, cubed, okay, so that's the radius times the radius times the radius, so be careful there. By the way, in order to estimate that on a calculator, you would enter the number r, you would hit this little, what's called a caret, it's a weird symbol, I think it looks more like a mountain than a carrot. And then I would hit 3 and equals, right? And so that's how you could raise something to a power that isn't 2. So that's how we're going to deal with it. Make sure you can get your calculator to do that, by the way, with this example. So here we go. If I want to calculate the volume of the sphere shown, I'm going to have the volume is equal to 4 divided by 3. Careful with your fraction work here, too. Really easy to plug this in wrong. You could actually multiply all of your numerator first and then divide by 3 at the end. So 4/3 pi r cubed, in this case, I happen to know r is 5 and cubed like so. So I'm going to do, remember, exponents first. So that's going to be 4/3 times pi. 5 cubed means 5 times 5 times 5, right? So side note, 5 times 5 times 5. These first two, that's 25, and 25 times 5 is 125. But you can also just, like I said, just do 5 caret button 3 equals, and we would get 125. And so for me, my next step, I usually would take this number and multiply by the numerator, and 125 times 4 would be 400 plus 100, 500. and leave that 3 there, multiplied by pi. So this is the exact answer, but let's get a decimal approximation here. So I could do 500 multiplied by pi and then divide by 3, or on my calculator I could do 500 divide by 3, right, maybe hit equal sign if I want, and then multiply by pi. Bunch of different ways I could do it. So let's get an approximation here. 500 divided by 3 multiplied by pi, and I'm ignoring their little thing there and there. So my answer is 523.60, and this is a volume. It's cubic units that are going into it, and since the radius was in inches, this would be in inches cubed. All right, and so that tells me how many little cubes could fill that solid. Okay, so that tells me how much space it takes up. And so this was in our first foldable like this, so we can kind of check that off. We did some of these other ones on a previous day. Let's go to another concept, which is surface area. So instead of knowing how much I fill this object, surface area is going to ask, right, how much wrapping paper would it take to wrap around the object? So surface area is, right, how many little square units, not cubic units, would it take to, right, completely surround that object? How much paint would it take to paint the object or carpet the planet, sort of thing like that. And so surface area is going to also be an interesting formula. But there's some explanations that I think are kind of amusing for the origin of it. By the way, we're gonna be doing this one right there in this foldable. So look out! I've got like 2 foldables going on. Pardon me if that's annoying. But one of the ways you can consider surface area of a sphere is that imagine, right? I've got a sphere here. It happens to look like I'm assuming a softball. And if you unstitch that softball, you would have 2 things that look like this. And notice, oddly enough, it's as though I've got kind of 4 circular parts there. And the area of the surface area of a sphere, actually, I think I write that in yellow. Surface area of a sphere happens to be 4 times pi r squared. And you might recall pi r squared, that's like the area of a single circle. And look at this, there happens to be 1, 2, 3, 4 of these. So it's kind of a nice little explanation. Oh, I ran out of undos. That's all right. So this is one explanation that I think makes it easy to remember the formula. So the surface area, right here, surface area is equal to just 4 pi r squared. Remember, exponent, square the radius before you multiply by the other parts. Here's another thing I can show you here. This one's actually a pretty fancy animation. Oh, there it goes. All right. So notice I've got on this object, I've got 4 of those red circles, and using looks like some sort of geometric projection, it's imagining this bottom circle, it's actually folding it up to cover the surface of that sphere. And it's trying to indicate that the areas of this little blue shape, this curvy surface, is exactly the same as the circular figure there. That is a circle. And notice that I have 1, 2, 3, 4 of these red circles around the sphere, and I would actually be able to have all 4 of them become those little triangular sheets that wrap it, and they would all 4 perfectly cover that sphere. So that's kind of an interesting little animation there. I think it's kind of pretty. I like it. Well done. Credits to Vincent Pantaloni for your wonderful work. So this formula, now that I know it, you don't necessarily have to be able to explain what it comes from. But to calculate it, not that bad. So its surface area is equal to 4 times pi times, in this case, 5 is my radius squared. And remember, squaring something, there's a square button on the calculator. You also could use caret 2, or you could just do 5 times 5. It's not 10. Careful, 25. And so this is equal to 25 times 4 is 100. So this is 100 pies. And so my surface area is approximately 314.3.14159. Now I realize I don't know the next digit of pi. How embarrassing. Because I don't know if I should round up or not. Tell you what, I'm going to do hundo pi in this. That's man, all these pi fans are going crazy. Oh, even more crazy. I did it wrong. 3.14159. Shame. Shame. So this would be 314.16. To completely ignore their rounding, I like rounding to the hundredths place. And this would be in inches squared. Okay, because it's surface area, right? So it's a two-dimensional measurement that represents the number of little squares, not cubes, squares that would wrap around that surface. Okay? So so those two foldables kind of complete out our set. So now we've got the volume of a sphere and the surface area of a sphere. I also have a big ideas video for section 11.8 in their geometry book that goes through some additional examples, particularly for the geometric solid of a sphere. So check that out as well if you'd like. Thanks for watching, internet friends. Adios.